Hey guys, I wanted to do a quick video on adding custom user sounds to your Lock Sound boards, right? And specifically Lock Sound 5 Select Direct is what I'm using in this video. If you saw the video that kind of played before this, it's the Metra engine Akata with the Lock Sound 5 board in it, a Lock Sound Select Direct, and I've added my custom sounds to it, and then you've kind of heard the station sounds that I've added, the now approaching, next stop, door closing, so forth. Those are all examples of custom sounds that I've added to an existing sound set. And so what you're seeing on my screen right now, this is Lock Programmer. I won't talk too much about all the other functions of Lock Programmer because there's other videos for that. I'm going to focus specifically on the sound tab. And then basically what I started with was a sound set that I got from Lock Programmer for an F40PH. I think it was an Amtrak version. It was updated for V5 board, and then I used that as my starting basis, and then I just kind of added to it. And so basically, I think the first thing that you would probably want to learn is, how do we get custom sounds into Lock Programmer? And so you see down here, I have this folder called Metra Sound, and then these are the different sound files. And so what you can do is go to Sound, add sound files, and then you would select your sound files. And so in this case, I'm going to do multiple, or you can do one. Then you would hit open. Okay, I'm not going to do it here because I already did it, but once you hit open, you'll see them kind of migrate over to this right pane. And this is kind of reflective of all the sound files that are now in the Lock Programmer at your disposal. And then if you're keeping a close eye on maximum capacity, current capacity, free capacity, this is the board and how much capacity it has now. Make sure you're watching that because that is actually what's going to dictate how many custom sounds you can put into your sound file because there's only so much free space, right? And so my files have made it in here, and then once they're in here, you'll see in the sound schedules, now we can actually select them from our drop downs. And so I'll actually talk about that in a second. So real quick, sound type of diesel, this is a diesel engine, not a steam. And so that'll actually gray out some settings in the sound schedules because it's not a steam. Sound slots, I think everyone's probably familiar with sound slots and how they work. And if you were to go to the decoder tab and functions, you'd see you can assign a sound slot to a function, and basically that sound schedule then starts to play when that function is engaged, and that's pretty standard basis. One other note quickly is if you see these don't have the sound slot prefix. That means they're kind of reserved names. They're meant for very specific functions. Break sound, this is a very specific sound schedule for break sounds, and this kind of, the decoder is looking for that sound slot to satisfy that. And same thing for gear shift sound, I'm not using that, but again, the decoder is looking for these reserved names. There's also one called random sounds, it's not showing up in here. I kind of created my own in a sound slot, but I read in the documentation that there is one called random sounds. I'm not sure what the scenario is to get that to show or what, but I haven't seen it, or if the documentation is just old and doesn't exist, but I've seen random sounds mentioned in a reserved name as well. Before I talk about my Metra sounds, I want to talk about this EMD late exhaust HEP, right? This is kind of the engine sound, and I feel like this is what people who are in here exploring, if they see something like this, they're like daunted by this and they get scared and they're kind of don't want to do anything else because this looks crazy. And yeah, I think I understand that and I agree with that. And so what I did is when I was first looking at how to do custom user sounds, there wasn't, like I said, there wasn't too many videos about it or documentation. So the best way to learn is to kind of unravel and look at an example, and that's kind of what I did here. And so if you're familiar with the engine and how it sounds, it's going through different phases, right? So there's manual startup, there's idle, there's high idle, and then there's the different gears, like D3, D4, D5, right? There's different notching and the different sounds of it ramping up and ramping down. And then basically you have like acceleration and deceleration sounds. If it goes from D3 to D4, it's going to ramp up, and then if it goes from D4 to D3, it's going to ramp down. That's everything that's going on in this, and it's very elaborate. The most important takeaway from this, though, for me, is it is setting a global variable called share1 and share2. That means that a global variable means it can be seen in all the other sound schedules. So when I was creating Metra sounds, I needed a way to trigger my logic on, right? Like, because everything's based on speed. When it speeds up, speeds down, it needs to make these sound announcements. And so instead of writing all my own logic, I wanted to to be tightly coupled in with the engine itself already, and so I'm using share one. So if you were to go through a lot of these different called states or containers, you would see that share one is getting set to a different value at different points in time. So as it gets, as it speeds up, share one increases. As it speeds down, share one decreases. When it's at high idle, share one is set to a standard value of 8. When it's at idle, it's set to 2, and so forth. So like just think like global variable share one. This sound schedule is setting it, so it's actually being used in multiple other places. One of those other places is this manual notching logic. Share one is definitely being used in there, and it's probably being used in fans and so forth. So just think of a global variable. So if we go into Metra sounds, now this looks a lot simpler, right? It's not, right? Once we go into these containers, you'll see more complex logic, but I've made sure that it's pretty much as logical and clean as possible, and so we'll kind of talk about that. And so let's back up and just talk about sound schedules in general, right? And so right now we're in the highest, let's say the highest level of the sound schedule, right? I have nothing selected, and so these are the properties for the sound schedule itself. So what's the name, the priority, unlimited versus notching, is it load dependent, and then these are the constant values. I have documentation that I'll attach a link to, and you can read more about priority, unlimited notching, load dependent, etc. I won't get too much into those today because I don't really use those much in this particular sound schedule, but you may need to use them in yours. So we'll kind of skip to the name for the sound slot. That's what's going to show up in the overview and show up in the function tab when you're assigning it to a function. And then constant values. Now if you're not into programming, these are basically values that don't change. They're constant, right, for lack of a better word. And it basically allows you to assign a more human readable name to an integer that could mean nothing to you. So when I'm actually programming my logic, it's easier for me to remember share one high idle versus remembering 8, right? And the nice thing Lock Programmer actually did is, if you were to go delete one of these and it was being leveraged in your sound schedule, it's going to give you a warning saying, hey, that's being used, you can't delete it, which I thought that was really, really cool. And so that's the highest level. And then if you were to go and select this, which is the state, you'll see this is going to change. So this is very much contingent on what's selected. So if nothing's selected, you're at the highest level. If any of these nodes are selected, then these are the properties for that node. And so right now mute is selected. Mute is a state, and so these are kind of your building blocks right here. If you select any of these, it'll create a new node or a new instance of a transition or container, and that's where you assign logic. Now, won't talk too much about clicking these because I've already done that, but you can kind of play around with that and click them and see that it'll create a new state, and then you can then create another state and then drag that, and then you link states by taking a transition and dragging from one to the next, right? It's as simple as that. So I'll delete these. And so back to this. So every sound schedule is going to start with mute, right? And then mute can either be preceded by logic, which say, okay, don't do anything until this logic is met, or mute can go straight into a state that played a sound, and then as soon as the board has power, that sound will start playing. Now that works for some cases, but for Metra sounds, I have it tied to a function, just because I want more control. And so what that mean is, so this state of mute has the outgoing transition that has a condition on it. That condition is function equals true. That means I cannot advance from this state to this state until this function is met, or this condition is met. Function refers to whatever function this sound schedule gets assigned to in the decoder setting. So right now I have this sound schedule set to function 16, and so that means once function 16 is engaged, this condition becomes true, then it moves on to the next state. This state right here, I've seen it used in a couple different other sound schedules. It's kind of a normal convention to then do more logic, right? It's not actually playing a sound. It's basically a way to kind of create a program loop to then wait for other conditions to either turn on or off, and then do more logic. So this one I'm just calling silence, wait for function. So this is then from mute to silence. Now silence has two legs to it. It's either going station sounds or route sounds. So when you saw in the video before, I have this thing called station sounds. That's like when the train is like basically sitting at Chicago Union Station and you hear like the track 14, track 16, track 14. You know, these are kind of the sounds that you hear when you're at the station. And so it's basically saying, and we're going back to these global variables again, right? If share 1 is less than share 1 idle, you know, this can proceed to station sounds. And so share 1 idle, you know, if you remember to the constants, I think that maps to 2. And then basically if function 8 isn't turned on, that's 0. At that point, share 1 is 0. And so it'll go right over here to station sounds. So station sound is a container, right? And so remember I was telling you about their states, transitions, containers. Containers means you can tap into it. And this is essentially a subroutine. All these kind of containers, they basically have an init and an end, or start and an end, and the end has to be satisfied, or else you'll get warnings or errors, and that's where this kind of validate comes into play, and I'll kind of explain that in a little bit. But basically, whenever you're building anything, make sure you hit validate, and if you have red checks, you need to fix those before trying to deploy, or else your program will crash or things won't work nicely. So always validate. So back to this kind of container. So containers allow you to keep related things kind of more tightly coupled. And so instead of having this logic thrown back into here, because I want this nice and simple, it's in this container. And then this is basically just a way for me to do those sounds of the station. So if I go to simulator, which we were talking about earlier, and I just hit function, you'll see that it's going to go through it.
Track number 16.
And loop, and so forth. So basically, each of these has a different sound associated to them. As soon as the sound is done playing, it advances to the next, advance to the next, advance to the next, loop back, right? It's a very simple loop, and I split it up into 4 shorter parts so that if it did need to exit based on logic, it was more instantaneous, right? If these were one long clip, and then you know, the user did something with the remote to change a condition, it would have to wait for this logic, or for the sound clip to end playing before it then execute a new logic and exited, where I want it to be able to exit quicker. And so in the normal flow, it goes from play, Metra 1, Metra 2, Metra 3, Metra 4, loop. And then basically what it's doing is looking for this condition to say, at any point in time, if share 1 becomes greater or equal than share 1 idle, so if the user presses function 8 and the engine starts to turn on, we need to exit out of this because we need to go to the route sounds. And so you see that each of these has that logic leg to go to this endpoint, which then kicks you back out to its parent. And so it will execute that after each time it plays. And then if it doesn't, it's able to then loop back. And then at some point, you know, they'll play indefinitely if the user never starts the engine up, or when the user starts the engine up, it'll go out. And then once it goes out, it then goes back to our silence loop, right? This one is no longer applicable. This is not true anymore, so it won't go here. This one then becomes true, and so it's going to go into route sounds. This is red because there's a sound function linked to something, one of the child nodes in there. But this is also a container as well, called route sounds. So I'm going to go into their route sounds, and so you'll see that this is a little more complex, but not crazy. It's not like the HEP one I showed you first. And I try to keep it more clean and organized, so I'm zooming out so you can see. So again, you know, we're in a container, so you have a logical starting point. And then for the Metra sounds, we have the pre-board announcements. This is a container, so you can have containers in containers, right? Yeah, you can get crazy, but logically it makes sense. Containers in containers, so pre-board announcements. So this is the first thing that's going to execute. So we'll drill into pre-board announcements. And this is just a simple logic chain that's, you know, again, starting with play. And then I have 2 logic chains straight after play. Basically looking at the direction of the engine. What's the current direction? Because as you know, with station sounds, there's inbound announcement and an outbound announcement. And so based on the direction, and we know about the Metra trains, you know, if they're depending on the way the engine's facing, you know, it's going inbound, outbound, and we wanted to make sure that was accurate and realistic. And so this will play. It'll look at both of these. Only one of these is going to be true. If it's in reverse, it'll go this way. If it's not in reverse, it'll go this way, and then they kind of diverge back because the safety message is common across both. So only the announcement, the pre-board announcement is different, and then the safety message is the same, so it can come back. Doesn't need 2 separate. And so you see right here, it's condition reverse equals true, and it goes to the state to play the sound, and you'll see here I have the sound, I have the simulator on, so that's why it's grayed out if I turn that on off. You'll see here's all my sounds that I can apply to this. So right now it's Metra inbound sound, and then basically when it's done playing, it's going to execute this transition. Now this transition has something we haven't talked about yet. It has an action associated with it. So an action is basically a way to set data. So everything else we've been doing up to this point, we've been reading data values. Now we're actually going to set a data value. And so what I wanted to do is I didn't want the safety message to play right away. And a couple different iterations of this logic, I actually had the safety message tied to speed settings, but then I wanted to remove the complexity, and I just wanted to play after a timer to make it more simplistic. So this is basically saying, as soon as the inbound announcement's done playing, set a timer. The timer is set to safety message delay. That is a constant that I set in the topmost level, because that's where you define constant. Safety message delay is 30, so that's 30 seconds. So I go back here, so then this silence is going to wait for 30 seconds, right? Because this logic condition isn't true yet. So this condition basically is timer equals 0. So as soon as this is set to 30, then it's going to count down 30, 29, 28, 27, and so forth. And this is just waiting, waiting, waiting. And once it gets to 0, then it's like, oh, hey, this condition is now true because timer equals 0. We can advance. This will then advance to safety message, which will play as soon as safety message is done playing, because it's not. And remember, because things aren't looping, they proceed on. So any of these that don't have this loop check, they will play, and then they will proceed on with logic. Only the ones that have loop basically will repeat themselves unless there's a logical exit point. So again, timer equals 0, so go to safety message plays once, it's not a loop. Once it's done playing, there's no conditions on these exit legs, done playing, exit. So this then exits back out to route sounds. So then this container is satisfied and fulfilled. And then from there, I have 2 logic points, right? So again, I'm looking at the direction of the chain because it's important to my logic down here and how I proceed. And so basically what I'm doing is, again, 2 legs. One is reverse equals true, one is reverse equals false. And then I just have these points where I can set these actions. And this one basically is saying if it's an inbound train, set user 1 to 1. And if it's an outbound train, set user 1 to 4. Again, user 1, 2, 3, and 4, those 4 variables are specific to sound schedules. They're not accessible anywhere else. We were talking about share 1 and share 2 earlier. Those are global. User 1, user 2, user 3, user 4, those are local or specific to the sound schedule. And so they can only be accessed here, and they don't affect anything in any other sound schedule. And so why am I setting this to 1 or 4? Basically, I wanted to keep this logic where I didn't have redundancy, right? And so I could easily have created containers that had Aurora, Naperville, Lisle, Belmont, Downers Grove, Union Station in one direction, and then another container that went Union Station, Downers Grove, the other direction, right? But I didn't want to do that because I don't want to be making change. I don't have to make changes to multiple things if I'm optimizing things. I want everything to be done in one place. So basically what I'm doing is an increment, decrement logic. And so basically I set this to 1. If you were to go through these and assign these integer values, this is 0, 1, 2, 3, 4, 5. So basically starting at 1, because it's inbound, after it did the pre-board announcement where it's saying inbound train, which means it's going from Aurora to Chicago, doesn't need to announce Aurora anymore because it's at Aurora, so it's starting at 1. So basically when it goes through this logic, Naperville will be the first stop. And then kind of the inverse, I'm setting it to 4, which means it'll start at Downers Grove. Now that's also important because once it kind of gets through this core logic, it then will determine whether it decrements. So right here you'll see user 1 plus 1, or if it increments user 1 plus 1, or decrements user 1 minus 1 to determine whether to go left to right or right to left. And I'll elaborate more on that in a second. So let's just go back to kind of where we were. So these legs, transitions are setting user 1 to 1 and user 1 to 4. Now I have these kind of speed gates that I'm calling, and then this direction logic is basically the start of my loop. for each kind of station where it's doing the now approaching and the next stop and the door closing. This is kind of the loop that it goes back to, and you'll kind of see how it feeds back into it once we go through this. So just think of that's kind of, once I've set the direction and I have those variables set, then I have my direction logic loop, which then starts waiting for conditions. And those conditions are basically speed. And so what I'm doing is I'm waiting for the Metra engine to reach a certain speed before I say it's eligible to start making station stops or announcements. And I do that each time. So that's because that's the second step in the loop. So you'll see that it's done each time this thing loops over. So basically the train has to speed up to, say, 60 miles an hour, and then once it hits 60, if it starts decelerating, then it will start making the announcements. And then once it goes to 0 and stops, and then it has to speed up again to 60, and then start decreasing before it makes it. Just a way to keep it more realistic and kind of, more predictable. And so that's what these speed gates, I'm calling them, are. So the first speed gate is called acceleration. It's waiting for share 1 to be greater or equal than share 1 d7. So that's, if you remember the HEP example, the speed has to get all the way to this d7, which then sets you share 1. And then once that's set, my loop, because this is looping, this direction logic, then this becomes true. So then it moves on to speed gate 2, or the second node, which is then waiting for what I call speed gate 2, deceleration. So now basically this one is saying, it met the speed, and so now we can proceed. Like I'm saying, the train went as fast as it was supposed to. It got up to a certain speed, so now we can actually proceed. Now we're going to wait for the train to slow down, and then now this is saying if share 1 is less than share 1 d7. So again, back to the HEP. Once the engine starts slowing down, share 1 value will change, and then this condition will become true. Then what it's doing is, if we remember back to here where I was saying user 1 got set to 1, user 1 got set to 4, each of these is assigned. So basically, if we're going down this path of inbound, user 1 is set to 1. So then each of these has a leg of is user 1 equals 0, user 1 equals 1, user 1 equals 2, 3, and 4, 5, you get it. So in this case, user 1 equals 1, so it's going to go to Naperville. And you're like, oh, what about Aurora? Well, again, if it's starting in Aurora, it doesn't need to go to Aurora. Aurora's only used in the reverse flow, and the same is true for Union Station. It's only used in this flow. So it'll go from Naperville to Union Station. In the outbound flow, it would go, from Downers Grove to Aurora, basically from an announcement standpoint. So user 1 equals 1, that condition, is true. And in the simulator, you can see all this, how it works and how the users change, and it's very cool. And I'll run through that real quick. So user 1 equals 1. Naperville is a container, just like the other ones I've shown you. Again, we've talked about this, where it's the entry and the exit, and then basically these are states, and this state has a sound map to it. So it's next equals Naperville. Then once it's done playing, I have a speed gate in here as well, because for more realism, I wanted to say, well, the next stop will be Naperville, and I immediately don't want to say now approaching Naperville. I wanted to wait for some other event, and that other event is another speed gate, basically. So it's saying if share 1 now is less than d5. So if you saw that the other one was d7, so now it has to go even slower. It has to be less than d5. And once this condition is met, it'll say the now approaching. And then once that plays, it'll exit out. And so this is pretty simple logic. And then it comes back, so once it exits out, it comes back to here, to this leg, right? Because it's exit out of the container. And then more speed gates, right? So I have all these speed gates for realism. So basically this is looking for it to stop to 0. So the logic is if share 1 is less than high idle gets set in the HEP schedule, sound schedule, and that equates to like 8. I think the integer of 8, and so basically I'm saying if in high idle the engine is stopped, right? It's sitting there idling, and that's what I want, right? And so once it's stopped fully, then I advance on to the speed gate, which is I'm saying I have these little hints on here like acceleration, deceleration, speed to 0, acceleration. So then I'm saying when the engine now accelerates again, look at this speed gate. So now I'm saying share 1 is greater than high idle. And why am I doing that? Because I want the door closing. I want the door closing sound to only play when the engine has reached 0, so it's come to a full stop. People have gotten off. And then once the engine starts up again, now I want the door closing to execute. So then that's why I'm looking for a concrete, yes, the engine stopped, and then yes, the engine now is greater than high idle. So it's not idling anymore, it's actually moving. Once it starts moving, I want to play this door closing sound. And then as a caveat, you'll see these little red. That means I have a mapping to another sound tied to these nodes. And that basically means while these nodes are active, it will then engage this sound slot. And this is the bell. So if you were watching the video before, you saw when it was kind of saying next stop, I think it's when now approaching, and it stops, that bell starts playing, which is kind of more realistic. When the trains are stopping at the stations, they play that bell for safety. I had that logic changed before to speed, but then for simplicity, I just linked it to other nodes. You can get more realistic by tying it to speeds, if you wanted the bell to continue playing until it met a certain speed, so forth. But I just have these tied to these nodes. So that red means that, again, mapping to a different sound, and that's playing while these are active. And once they've advanced, they stop. The sound will stop. That associated sound will stop. So once the door closing sound is done, it then evaluates these two legs, right? And these two legs are basically, again, that reverse logic. I'm always evaluating the train condition. I mean, I probably could optimize this by checking the direction once and then setting like user 3 to an integer and just use that. But this works for me. So again, we're in this flow, the inbound flow. So this leg executes to be true. So then it goes to inbound next, which is just a logical state. And then the offshoot of that, remember I was telling you, it goes back to this loop. And so it comes right up here. What it's doing though is it's setting an action. So it comes down here, set this action, user 1 plus equals 1 or plus 1, depending on how you want to say it. So basically, if user 1 was 1, at this point user 1 becomes 2. And that is what's allowing us to go from Naperville to Lisle. So now user 1, so now when we come back to the starting point of this loop, user 1 now equals 2. We'll wait for our speed gates, our acceleration, deceleration, and then this logic will say user 1 is 2, go to Lisle. Go into Lisle container, do the approaching, do the next, go to speed gate, door closing, come back, user 1 will equal 3. So you get it, right? It's incrementing through, and that's how that's done, by this action right here. Actions, just to elaborate on that, set timers, shares, and users, right? That's how we set those values. One thing that I haven't talked about here, but I'll quickly kind of cover, is selects. So I'm not using any selects here. There's selects 1 through 6, and those are, you can tie those to functions. And so like the share 1 and share 2, those are being set in sound schedules. Selects can be sound at the function level. So if you were to go into decoder and then go into a function mapping, and then you could do a drop down. See if this loads. I don't have anything connected to the lock programmer. So this is gonna, oh, it did load. So I guess you don't need to. So if you were to come down here, so you have your sound slots, right? And then, but here in logical functions, you'll see the shift modes. Did I say select? I meant shift. These are where you're setting these shift modes. So there's 1 through 6, shift 1, shift 2, shift 3, shift 4, shift 5, shift 6. I didn't need to go through those, but I did. You can use those in here, and so you can tie a kind of a logical hardware function with function into this sound schedule. And so I'll show you, like in the condition, you can send, and shifts are all true or false, right? So here's like the complete list of conditions you can play off of, which I didn't really talk about that. And so speed, requested speed, acceleration, timer, function, which is true or false, reverse true or false, shift 1 through 6 are true or false, share 1 and 2 probably have a value of 0 to 255. I didn't use the breaks. User 1 through 4 again, and then sound CVs. The sound CVs are, you're able to set those at the CV level. So those are mostly I've seen used for like changing horns and bells. And so without having to make the user come in and mess around with the sound schedule, someone could create a sound schedule that uses the sound CVs, and then they could just change those CVs with their remote and not have to worry about any of this stuff. And those are actually defined in decoder sound slot settings, and then you'll see here's the CVs and their current values. And so like if you were to change these at your remote level, then you could then inspect that sound CV in here and do logic on it. But I think that's more advanced, and if you have any questions, just ask me about that. I can talk more about that, and I'll give you an example before I stop this video on how that works. And so back to this loop, and if you were to then change the direction, it would then just go this way and execute this way, and then decrement going from 5, 4, 3, 2, 1, and then so forth. And then what I'm doing is when you get to Aurora and when you get to Union Station, instead of it going out back to the loop, it basically goes the other way and goes out to stop. Or basically, remember I was saying this, we're in a container basically, and it goes back to its parent. So I have this route complete logic, which is basically saying if it goes back to idling or less than idle, which is share one idle I think is equal to 2, and so if you essentially shut off function 8, it will exit. If you don't shut off function 8, the engine is just going to sit there quietly because it's kind of stuck in this route complete. So I don't want when it says next stop is Aurora and then now approaching Aurora, you're essentially stopped at Aurora, which is the last stop. And so I just want the engine to kind of sit there quietly. And the engine's still running at this point, because if it wasn't running, it would execute. Once the engine stops, the user toggles F8, then this will fire, and then it actually goes out back to our main container, goes back to this loop, and then because share 1 now is less than the idle 1, which was that main condition to exit, station sounds start playing again. So you'll start hearing the 14, 16, whatever. Could probably do different sounds based on what direction, because I'm sure the Aurora yard sounds a lot different than Union Station, but I didn't add that in here, but that's very easy to do and very possible. So yeah, that's kind of the overview of Metra sounds. The only other thing that I added was I have my own thing called random sounds. So if you saw in the video before, when the engine's kind of just sitting there at the station and it hasn't, there's no speed, it's kind of idling, whatever. I just wanted these random, air let-offs and sanding valves just to make it, more, sound better. So it's like it's sitting there and it's, making like spinning like noises randomly. And this is pretty simple logic where it's, starting from mute. I have this mapped to a function, so Metra sounds and random sounds are both mapped to function 16. So when I turn on Metra sounds, random sounds also goes on. And this basically goes to a function called pick random. This is a logic only state. And then pick random, basically the LATE coming into it is setting user 1 to random, and this is 1 to 2. So this is a mini function. I actually don't know what other functions are available. I think this is the one I've seen in documentation. So rand, and then starting point, end point. So I only have these 2 sounds. So I'm only saying pick a random number from 1 to 2. So it's either going to go this sound or this sound. And then I'm also, I think I'm also randomizing the timer. Yeah, because I don't want it to every 10 seconds play a random sound. I want it to be more random. So then this one's saying pick up random seconds from 10 seconds to 60 seconds to then go back and execute the loop. So think about it, go from mute, function is enabled, goes to silence, and then silence goes to pick a random number picks either one of these, it plays it, then this sets a timer, the timer is set to a random 10 to 60 seconds, then once this, because this leg has the timer has to be equal to 0 before you, so this is basically waiting for the timer, and then it goes back and loops, and that's how you just get these random sounds. So that's pretty cool. We'll talk about the simulator real quick. And so if I go into this HEP sound and I open the simulator, and you'll see I've been talking about this mute and function thing a ton of times, like mute. So basically when the simulator is open, this green is basically where it's at in the code or in the execution. You know, let me go to Metra sounds because it's simpler to understand. So we'll come here, toggle off simulator, toggle on simulator. Okay, so mute is, and if I hit function, which again is function 16 for me, you see how it quickly went to silence, and then it saw that share 1 was less than share 1 idle, so then it quickly went over to station sounds, started placing station sounds, and then you'll see I'll change share 1 in here, and you'll see how it kind of equates. So I'll hit function again, quickly, and then I'll adjust share 1 to be greater.
Track number 16. Track number 14. Track number 16. BNSF, train number 1235, scheduled to depart at 2:30 to Aurora, with intermediate stops at Downers.
So yeah, you see how I adjusted share 1 to be greater than, I think it was 8 I needed to go to. I thought it was 2, but I think it was, no, it was 6. Share 1, idle is 6. Startup is 2, idle is 6, high idle is 8. So the first was always 2, but then as soon as I made it greater than 6, it then exited station sound, went back to silence. This became true and went to route sound, started playing them. So you can see how the simulator works. And then lastly, before I'll talk about, remember I was talking about those sound CVs. I think it's a good thing to talk about. So here's a horn. See, this is mapped, all these conditional legs are mapped to the sound CV. So this one's 9, this one, it's hard to see these, 9 equals 1, 9 equals 2, and so forth. And so this is a sound schedule that's tied to the sound CV, which a user can change from their remote just by setting a CV value and not have to come in here. And then real quick, let me talk about some of these other settings. So in this property inspector, you have sample, or we'll go from the top, state property. So this is the name, shows up here. Sample means if it is a non-log, if it's not just logic, but it actually plays a sound. This is where you select the sound. General cylinder is grayed out because I'm in a diesel project, but if you were in a steam projects, you would be able to see this. And cylinder is basically what cylinder it's in for this to play, and then speed. What speed should I play back the sound at? Speed is an option setting located on the right. Value is 0 to 255. Speed is set. The option will not allow the state to play unless the decoder speed is higher than the sound setting. So it's basically a condition to say don't play the sound unless the speed is set. Repeat playback is where I was setting the loop. This is basically how many times it should loop. So this is infinitely. If you were to change these values, it would only loop 4 times, 5 times, or whatever. So this is an infinite loop. Volume, you can control more granular volume settings, and so this can be less than the master volume, which is set at the decoder level. Pitch range, so you can change pitch. Smoke, if you want to change smoke characteristics, if your engine has smoke. And then these flags basically have to do with like interruption and boarding and then drive lock. Like if the sound is playing, don't allow the engine to move. And you see if I hovered over it, it essentially tells you what it does. Stop the motor while the sound is playing. Don't allow the train to start while the sound is playing. And then you have abort, stop sound immediately when turning off the function. And then restore is basically, I think it has to do with priority. If something with a greater priority interrupts it, should then go back and play. Let's see, restore sound play. We'll start here if the sound was interrupted previously by priority conflict. So that's basically saying continue the sound if it was interrupted. I'll put the documentation that I've been using for this into this video. So yeah, that's kind of the overview of the sounds. The other one thing maybe to mention is some of those sounds, I originally wanted to record them from the Metra itself, but there was a lot of noise and background noise, and so I didn't want that in my video, in my train. So I actually came up with kind of I think it's clever, but kind of a different way to record those sounds. And so I'm basically using text to speech to then create all these sounds. So I come up with these. You can highlight over this, and then you can do the speech, start speaking. and then basically it
The next stop will be Downers Grove, Main Street.
So then, I'm basically then using a program like Audacity to record that text to speech, and then using Audacity, then I can control the, tempo and pitch and tone and all that to then make it sound more mechanical or make it sound slower or faster, trying to match Metra as close as possible. I use Audacity to edit those, and then I brought them back to Lock Programmer. In the future, I might try to record them again from the train, and then all I have to do is swap out the WAV files and then redeploy the sound. But right now, I'm kind of happy with it, and I think it's okay. And then, so once you've done with your sound schedule, you've hit validate 100 times to make sure everything is green. You then need to deploy the sounds to the actual engine, and so that's where write sound data comes in. This actually, if I'm sure if you're using this program, you know about this. So this will actually write the sound data to the engine. It takes about 30 minutes each time. So when you're developing these sound schedules, use the simulator as much as possible because you don't want to deploy every 30 minutes to test your sound schedule. Now I will say there, like anything in coding, there's a difference between a simulator and an actual device. So code as much as you can in the simulator till you get it to a point where you're feeling good about it. Deploy it on your actual train and then test on there. And then I'm sure you'll see the subtle nuances that you might want to change because, again, the simulator's not 100%. Like, there's different characteristics on acceleration, deceleration, and so forth. So, yeah, if you have any other questions, please reach out and let me know. Other than that, thanks for listening to me ramble.